Now let's discuss the second effect, and that is the effect of rotation of Earth on its gravity. So on this particular graph, you can see that the value of G, gravitational acceleration in SI system, or on the other side, the same value in the US customary units, is plotted on y-axis, and you have the latitude in degrees on x-axis, right? So the effect of rotation is not constant anywhere on the surface. It depends on where you are actually on the surface of Earth. When you are at equator, that effect will be maximum, and when you are at one of the poles, that effect will be the minimum, right? And that effect is actually a reduction in the force of gravity and gravitational acceleration, right? So that reduction actually is maximum at the equator, which have a latitude equal to 0. So all along this line, which is equator, if you lie there, you will be experiencing the maximum effect of Earth's rotation on gravity, right? But if you happen to lie on any pole, for example, North Pole, that effect will be negligible. Actually, the values at those poles will be same as the values if there was no rotation of Earth, right? So the effect of rotation of Earth on the gravitational acceleration is described by a formula called International Gravity Formula, this one, and it is describing you the value of small g as a function of your latitude, actually where you are rotating on the globe, right? So if you know your latitude, you can put that in and you can exactly get the value of g while including the effect of rotation, right? If you plot that expression for all values of gamma, this latitude value starting from 0 degrees to 90 degrees, 90 degree means poles, 0 degree means equator, right? So you will get that red line, this line, and that is the value of G relative to rotating Earth, right? So this value starts from 9.78 at equator and goes up to more than 9.83. The difference, if you quantify actually, is very less. It is less than 1%, right? Or even less than 0.5%. But there is a correction you need to apply to the small value, small g, if you want to account for the rotation of Earth. There is another line which is relative to non-rotating Earth, like the value of g when you don't consider that effect of rotation. And you can see that that is described as this line. And that line is also not a constant value. So it means that even if you don't include the effect of Earth's rotation, the value of small g is not constant anywhere on the Earth. It depends on your location, right? And why that should be, why this second line, which I'm highlighting now, is not a constant line? Any ideas? Yes, please. Yes, exactly. That we don't have a perfect sphere here with a constant r value. Earth is an oblate shape, right? So therefore, you have more value of the distance at equator compared to at poles. Yes, please. For most practical applications, you may have a value called standard value of G, right? So not in all problems you need to correct that small value of G based on your location. So there is a standard value of G also, which if not mentioned in a particular problem, you can use. And I will introduce that standard value in a moment. So the difference between both of these lines is actually due to the Earth's rotation, right? And that effect becomes negligible as you go to poles, and it is more pronounced as you come towards the equator. And that difference mathematically is equal to this quantity. In SI units, it is equal to 3.382 times 10 raised to power minus 2 multiplied by cos square gamma, where gamma is the value of your latitude in degrees, right? So this will be the difference in the gravitational acceleration between when you consider the effect of rotation versus when you don't consider. So if you have the top line, you can subtract this quantity for all values of gamma to get a bottom line. Or if you have the bottom line, you can add that quantity to get the top line. So in certain problems, you may be asked to explicitly account for that effect of rotation. So in that case, you may need to apply this international gravity formula. And in that case, you may need to know exactly your latitude in order to use that expression, right? So think of this reduction in the gravitational acceleration as a kind of the effect of centrifugal force which Earth is applying to like throw you out of its like surface, right? And but that effect is negligible, as I said, that it is less than 0.5%. So unless you are dealing with very high precision problems, you generally don't consider that effect in many practical applications. However, there is an associated concept called apparent weight and a true weight. Obviously, when you determine the weight of an object using like a spring balance on the surface of Earth, you are accounting for that effect of rotation automatically, right? So that is called apparent weight, which you determine using an experiment on the surface, and it will be slightly less than its true weight. A true weight would be the weight corresponding to an Earth which was not rotating, right? The difference between them is due to the rotation of Earth. So please keep that terminology also in mind. The difference between both weights would be whether you account for the Earth's rotation or not. This is the standard value of G, which is mostly used in different problems. That if it is not asked to explicitly account for the effect of rotation, you can use the value of G corresponding to the rotating Earth, and you can use the value at sea level and corresponding to a latitude of 45 degrees. This actually, all three of them would result in this value of G for most practical applications, and therefore it is called the standard value of G in SI units. And similarly, this will be the value in the US units, right? So please keep that in mind that if you are not dealing with like explicit determination of a particular effect, use standard value of G.